I'm not supposed to use words like impossible in my field, but the first time I saw the raw data from ATLAS, later designated 3, I/ATLAS, I felt my chest tighten in a way numbers don't usually provoke. The light curve was wrong. Not off by a margin wrong, catastrophically, structurally, physically wrong. A coma shouldn't flicker like that unless something extreme is happening, and even then, nothing in the standard physics of volatile sublimation can produce such abrupt surges, dips, and stabilizations. It looked as if the object were adjusting to something. Within hours, colleagues from Keck forwarded higher resolution frames, multiple bright knots forming inside the coma, behaving like fragments tearing away. I've seen breakups before. Oumuamua had hints of non-gravitational acceleration. Borisov displayed a beautiful, chaotic disintegration near perihelion, but Atlas wasn't doing that. Its fragments weren't dispersing. They were lingering in formations that defied ballistic expectation, not drifting apart, not spiraling, just holding. I've studied anomalies my entire career, interstellar objects, cosmic shells, even hypothetical technosignatures, but this was the first time I saw something that made even my most conservative colleagues whisper words like non-natural. What I saw instead was an object breaking apart in a way that mirrored biological mitosis more than celestial fragmentation. A structure tearing itself open but refusing to fall apart. A system maintaining coherence after rupture. By the second night, the Hubble team reached out with something even more disturbing. The coma's brightness pattern wasn't random turbulence. It followed periodic surges like pulses, a heartbeat mapped onto dust and ice. I remember staring at the data in my office, lights off, screen glowing pale blue, and feeling something I hadn't felt since the early days of Oumuamua. The sensation that the universe was speaking in a language we hadn't learned yet. The next morning, I flew to the Cambridge Center for Astrophysics, where emergency channels buzzed nonstop. Everyone wanted answers. No one had any. A physicist I knew from Caltech waved me into a small analysis room, his eyes wide. "Avi, look at this," he said, projecting a set of coma temperature models onto the wall. "We detected thermal spikes coinciding with the fragmentation windows, but the spikes are too brief to be solar-driven. And watch this." He overlaid the orbital spread of the fragments. I frowned. The fragment velocities were wrong, too uniform, too damped, as if something were counteracting their natural dispersion. What force?" he asked. "There is none," I said. "None that we know." But that wasn't the moment that truly changed everything. That moment came 11 minutes later, when Keck released updated photometry. 4 fragments, newly registered, arranged in a loose, almost geometric cluster. I zoomed in, enhanced the edges, cross-checked against background noise. There was no mistake. The fragments maintained spacing within an error margin tighter than any natural debris field should allow. Something was holding them in proximity. A cohesive behavior that defied standard comet physics. Someone behind me whispered, "It's like it's holding itself together." Another voice added, "Or trying to." That sentence stuck with me the entire day, trying to. As if Atlas were not an inert rock and ice body mutilated by solar stress, but a system responding to internal stress with countermeasures. By late afternoon, rumors of an emergency IAU session spread. Data packets flew between institutions like frantic birds. And then, late in the evening, a file appeared in my inbox, a spectral thumbnail from Hubble's ultraviolet scan. I enlarged it slowly, my hands cold. There, embedded in the coma's emission lines, was a structural anomaly, an unexpected chemical imbalance that should not exist in a standard interstellar comet. Silicates, yes, carbonaceous traces expected, but interspersed between them were spikes, unidentified heavy elements with partial bonding signatures that resembled early-stage crystalline networks. A comet doesn't do that. A natural object doesn't decide which fragments remain and which disperse. Something inside Atlas was regulating the disintegration. Not preventing it, not reversing it, regulating it. I leaned back in my chair, heart pounding like I was 20 again, staring at extraterrestrial data for the first time. Whatever 3I/ATLAS was, it wasn't simply breaking, it was breaking with intention. When the emergency session of the IAU began, I already knew the room would fracture into two camps: those who clung to classical comet physics like a lifeline, and those who recognized that Atlas was rewriting every equation we'd inherited. I sat near the front, not because I wanted visibility, but because the tension in the room felt like a gravitational field, and I needed distance to think. The first presentations were predictable. Thermal models, orbital simulations, particle ejection analysis, none of them fit the observations. Every speaker sounded like they were trying to stitch old logic onto a phenomenon that refused to obey. I watched respected colleagues stumble through explanations they didn't believe in. A few tried to blame instrumentation errors, atmospheric noise, calibration faults, but you can't dismiss a global anomaly when 11 telescopes across 4 continents see the same impossible thing. When the chair finally nodded to me, I walked to the console with a sense of inevitability. I projected the fragment spacing data, updated, cleaner, and more damning than ever. On the screen, the 4 major fragments hovered in a formation that resembled a loose tetrahedral array. The margins of deviation were so small they looked intentional, like the components of a machine keeping relative positions despite external turbulence. "This is not ballistic behavior," I said, my voice flat. "This is a system resisting entropy." A murmur rippled through the room. I saw fear in more eyes than skepticism. Before anyone could interrupt, I cued the spectroscopic data from Keck. The chemical signatures filled the display: silicates, carbon, volatile, and the anomalous bonding lines, the heavy element spikes, the flexible crystalline pattern that had no business existing in a fragile interstellar object. "These structures shouldn't appear in a comet," I said. "Not in any configuration we've ever observed. They behave like a material designed to redistribute stress, like a lattice that can temporarily destabilize and then reform." I hadn't expected anyone to support me, but that was when Ilara Vance, someone whose mind I trust, whose instincts rarely fail, stood and asked to speak. She didn't bother walking to the podium. Her voice carried anyway. "Atlas isn't just disintegrating," she said. "It's undergoing a reversible state transition." The room erupted. Theoretical astrophysicists arguing with solid-state physicists, observational astronomers clashing with chemists. Words like nonsense, speculation, and unfalsifiable flew like shrapnel, but Ilara continued. "There are materials that can self-repair on microscales, fracture, realign, reintegrate. We've engineered some ourselves. What if Atlas formed in an environment harsh enough to force similar behavior into its lattice at a natural cosmic scale?" I enlarged the Webb infrared spectrum, rotating the emission lines. The new data from JWST had arrived only hours before the meeting. Its sensitivity was unmatched, and the anomalies were undeniable now. There, buried in the thermal gradient, were signs of amorphous silicates behaving in a way we'd never catalogued, absorbing heat asymmetrically, delaying dispersion, distributing it across the surviving fragments like a network-sharing load. "It's not a comet," I said quietly. It's a cohesive entity." Someone near the back shouted, "Are you suggesting this thing is alive?" I shook my head. "Not alive, but not passive either." Ilara added, "Think of it as a material system capable of temporary structural dissolution and reassembly. Not biological, not mechanical, something else." For a moment, the room fell silent, as if everyone collectively realized the implications. If Atlas could temporarily break and then reconstruct itself, then it wasn't merely surviving interstellar space, it was adapted to it, engineered by nature in conditions we've never imagined. I projected the orbital decay plot, one more piece of evidence impossible to ignore. After the fragmentation, the fragments should have drifted apart indefinitely. Instead, the largest pieces were slowly converging. A natural object does not reverse dispersion. A natural object does not recall its fragments. I could feel my pulse in my temples as I delivered the final data set, the convergence vectors. They didn't align with solar radiation pressure or gravitational harmonics. They aligned with each other. The system was moving with coordinated intention, not intelligence, but intention. And for the first time since Atlas entered our solar system, the room stopped arguing and simply stared, each of us wondering the same impossible question. What kind of object can break itself, Joan, and then choose to come back together? When Atlas approached perihelion, every instrument on Earth and beyond was pointed at it. We all understood the stakes. If our theories were wrong, if its strange bonding patterns were coincidence, if the convergence vectors were flukes, then the sun would settle the debate by destroying the object completely. No material, no matter how exotic, survives that kind of thermal assault intact. But as the object drew closer to the sun, something unexpected happened. Its brightness didn't rise smoothly like a normal comet reacting to heat. It spiked violently, as if layers were shedding all at once. The coma expanded, then collapsed inward, then expanded again in a rhythm that made no physical sense. Multiple observatories reported simultaneous jets firing from different fragments, jets that weren't aligned with solar heating at all. They were directional, almost corrective. This isn't sublimation, I said during the joint monitoring session. This is a stress response. I watched the live photometry as Atlas crossed the threshold where standard comet models predict catastrophic fragmentation. The radiation pressure peaked, the thermal load surged, and then, exactly as predicted by the old physics, Atlas broke. Not partially, not gradually, it shattered. 4 major cores peeled away from each other like the petals of a collapsing star. A massive dust plume unfurled behind them, stretching millions of kilometers, long enough that for a moment I felt an old instinctual dread, like witnessing the death of something ancient. News outlets immediately declared it gone, broken, vaporized. But I couldn't accept that, not with what we'd already seen. I sat glued to the telemetry, breath shallow, as the 4 fragments continued outward on near-linear trajectories. Webb's infrared instruments tracked the thermal signature dropping rapidly as the fragments receded from the sun. "This is the end of it," someone whispered behind me. Then, 48 hours after perihelion, everything changed. The first alert came from the solar dynamics team. "We're detecting a flare," they said. "Not from the sun, from Atlas." I pulled up the data so fast my hands shook. Fragment C, one of the largest, had suddenly brightened by nearly a factor of 6. Not a reflective spike, not an outgassing pulse, a genuine high-energy flare. Within seconds, fragments A, B, and D responded, not simultaneously, but sequentially, as though reacting to the first one's emission. Their brightnesses rose sharply in a pattern too ordered for natural chaos. "What the hell is it doing?" someone asked. The dust plume that had stretched behind them, once a chaotic trail of debris, began thinning rapidly. Webb detected that its particle density was dropping at a rate far too fast for dispersion alone. "It's absorbing the dust," I said, barely hearing my own voice. We watched as the dust signature dwindled, and then dwindled more, until only a faint residual cloud remained. It wasn't drifting into space. It wasn't being blown away by radiation pressure. It was vanishing into the fragments. They weren't merely reforming, they were reclaiming themselves. "You're telling me it's putting itself back together?" a researcher asked, disbelief cracking her voice. "Not fully," I said, "but it's restoring structural mass." The convergence vectors updated automatically on my screen. And there it was, the unmistakable signal. The 4 major fragments were no longer drifting apart. Their tiny divergence angles had flattened. Their paths were bending ever so slightly back toward one another. "It survived perihelion," someone murmured. "It actually survived. No comet in recorded history, no interstellar object we've ever modeled, not even the hardened asteroidal bodies from the Oort cloud behave like that after complete fragmentation. The sun should have annihilated it. Instead, Atlas emerged like something wounded but still alive, reclaiming what it had lost, correcting itself, directing itself. The flare signatures reinforced this. They weren't random. They were tuned to specific wavelengths, bursts capable of heating and reactivating the flexible crystalline bonds we had theorized. Each burst correlated with a dip in fragment rotation speed, as if energy was being funneled into stabilizing the structure rather than emitting it. "This thing is operating like a self-healing system," Ilara said quietly beside me. "It isn't biological," I said. "It's material physics pushed into a regime we've never seen." "And it passed the ultimate test," she said. "The sun tried to break it, and it rebuilt." The room fell silent as the convergence plots stabilized into unmistakable arcs. The fragments were accelerating, minutely but undeniably, toward each other. The sun had not destroyed Atlas. It had revealed what Atlas truly was: a system capable of disassembly, a system capable of reassembly, a system that behaved less like a comet and more like a resilient interstellar construct shaped by environments we barely understand. For the first time in my career, I felt the scale of our ignorance like a physical weight. Because if one interstellar object could do this, the universe might be full of matter we've been too primitive to recognize. In the days that followed the perihelion event, the scientific community entered a phase I can only describe as cognitive dissonance at scale. The data forced a truth no one was prepared to confront. ATLAS was not approaching physics from our side of the equation. It was operating in a region of material behavior we had never mapped, never predicted, never imagined. Yet the evidence sat in front of us. Radiative flares functioning as trigger mechanisms, crystalline bonds reactivating at variable temperatures, fragments converging with mathematical precision. I spent most of those days in the analysis lab at Harvard, surrounded by projection screens filled with spectral lines, lattice models, and orbital reconstructions. And there, buried in the raw backside of the James Webb Space Telescope data, I saw what Ilara had been hinting at all along. "Look at the bonding geometry," she said, joining me at the console. "This isn't random network regeneration. It's programmable." The crystalline patterns showed flexible silicate matrices arranged in configurations that responded dynamically to stress. When heated, the bonds loosened, allowing fragmentation. When cooled, under specific radiative input, the network reformed, stronger, tighter, more aligned. "This is material with a memory," I said, "a lattice that remembers its previous arrangement." "But not perfectly," she replied. "It's iterative. Each fragmentation and reassembly improves internal stability. Self-improving matter, a horrifying and fascinating idea. We ran retrograde orbital simulations next, tracing ATLAS back across interstellar space. What the models revealed challenged even my most liberal expectations. Atlas had not wandered here randomly. Its velocity prior to solar capture suggested an origin far beyond the typical dispersal zones of planetary systems. The vector pointed toward a densely star-packed region, not a calm neighborhood like ours, but a binary system where two suns danced violently around each other. A place with massive gravitational oscillations, intense radiation bursts, and enough environmental stress to reshape matter at the molecular level. "In a system like that," Ilara said, "only materials capable of self-repair would survive long enough to escape." I stared at the simulated binary cluster rotating on the screen. If Atlas formed there, it would have endured conditions that tear ordinary comets into dust. Those conditions might not just select for resilience, they might create it. The implications were staggering. For decades, we assumed comet-like interstellar visitors were fragile, remnants of planetary formation, and sometimes they are. But Atlas wasn't fragile. It wasn't a remnant. It was a survivor of environments more violent than any our solar system had ever produced. What if this is a natural evolution of matter in extreme astrophysical nurseries? I asked. Not engineered, not alive, just selected. Self-assembling silicate networks would thrive there, Ilara said. They'd fracture under extreme heat, then rebind when conditions stabilize. Over millions of cycles, they'd develop flexible crystalline patterns that behave like an adaptive system. We weren't describing biology. We weren't describing technology. We were describing a new category, matter shaped by cosmic natural selection, a living material without life, a mechanical system without design, an entity forged from chaos, taught by the universe to outlast destruction. As we continued examining the spectral anomalies, another revelation surfaced. During each fragmentation cycle recorded by our telescopes, Atlas emitted faint but consistent low-frequency oscillations, vibrations encoded in its thermal signature like seismic patterns. Structural feedback, I whispered. It's analyzing the stress conditions during fragmentation. That means it's not simply functioning, Ilara replied. It's optimizing. The fragments' reconvergence confirmed this. The spacing between them was shrinking with each cycle, approaching a configuration more stable than the original body. Atlas wasn't just rebuilding, it was upgrading. The more I studied it, the more one conclusion pressed in on me from the edge of thought. Atlas was a laboratory, but not ours. It was a container of lessons forged over eons, a physical diary of survival written in the language of molecular architecture. And then the idea came, subtle at first, then overwhelming. What if objects like Atlas play a role in panspermia-like processes? I said. Not delivering biological life, but delivering material templates, structures capable of withstanding interstellar extremes. Seeds, Ilara said. Not seeds of life, but seeds of resilience. The term settled between us with the weight of a new paradigm. Atlas wasn't a comet. It wasn't an anomaly. It was a messenger from a region of the cosmos where matter is pushed to its limits and forced to adapt or perish. And now, after surviving our sun, it was demonstrating the full extent of its evolutionary mastery. We weren't observing a single event. We were witnessing the legacy of a star system, sculpting matter into a form capable of crossing galaxies. For the first time, I realized the most unsettling truth of all. ATLAS wasn't here to surprise us. It was here because objects like it survive long enough to be found. As Atlas drifted away from the sun, its fragments moving in slow, deliberate arcs toward one another, the enormity of what we were witnessing settled over the scientific world like a new gravitational field. The data streams now came less frantically, but with more reverence. Spectral files, thermal maps, convergence models, each one documenting the quiet reconstruction of something that defied every boundary we'd drawn around matter. I watched the convergence vectors update hourly. The four major cores were easing closer, millimeter by millimeter in astronomical terms, guided by forces we still couldn't fully quantify. The residual dust continued to decline as the fragments absorbed the last available material, knitting themselves back into a coherent structure. It wasn't perfect symmetry, but it was deliberate, purposeful, the slow return of an object that refused to die. In every meeting, every late-night discussion, one truth echoed between us. Atlas was teaching us a new grammar of physics, a system that could disassemble, survive catastrophic stress, and reassemble over and over again was not a visitor we could categorize, only one we could follow and learn from. By the time Atlas crossed Mars's orbit outbound, its structure had stabilized into something resembling its pre-perihelion state, but subtly refined, the fragments now locked together in a tighter crystalline arrangement. Its rotational period shortened, its thermal responses steadier, its brightness fluctuations minimized. It looked less like something recovering and more like something evolving. "This isn't a remnant," I said during one of the final briefings. "This is a blueprint." The team fell silent. We all understood what that meant. Atlas wasn't an isolated anomaly. It was an example of what matter becomes when shaped by cosmic extremes, an ambassador from regions of the galaxy where the rules of material survival are rewritten under unimaginable pressures. And now it was preparing to leave. As it accelerated outward, the sun's influence weakening, its trajectory sharpened, settling into a clean hyperbolic escape path. Atlas was returning to interstellar space, carrying with it the signature of its origin and the scars of its encounter with our star, scars that it had already partially healed. I watched its final visible light images from the Subaru telescope, a faint, steady point receding into the velvet of deep space. Not flickering, not fracturing, just moving, enduring. It struck me then that our solar system wasn't a destination for objects like Atlas. It was a checkpoint, a testing ground, a momentary environment in which its adaptive properties revealed themselves under stress. We weren't the first system to see it. or something like it, and we wouldn't be the last. The models predicted that Atlas would continue along its outbound course for millions of years, eventually drifting through another star system, and when it encountered new gravitational stress, new radiation patterns, new extremes, it might fracture again, it might reassemble again, it might refine itself further, a traveler whose body was its spacecraft, its shield, its experiment. As I looked at the final telemetry packet, one idea crystallized with stunning clarity. Atlas was not simply surviving the universe, it was participating in it, a form of matter that didn't just endure cosmic violence, but learned from it. A structure that didn't just drift through galaxies, but carried with it a record of every extreme it had weathered. A messenger, not in communication, but in demonstration. Atlas had come into our solar system as an enigma. It left as a revelation. And as its light faded from our instruments, I felt something I hadn't expected. Humility. A recognition that the universe does not need life to create resilience, does not need engineering to produce complexity. Sometimes the cosmos itself sculpts entities capable of defying destruction, carrying forward the lessons of stars long dead. The last data point blinked onto my screen, its position, its velocity, its diminishing signal, and then it was gone, slipping back into the abyss between suns. Atlas didn't stay to be understood. It stayed just long enough to show us how little we understand.